Well, hello, ladies and gentlemen. Those of you who were able to join me last night for our little WebEx meeting, we talked about ozone chemistry and ozone depletion. And you know what? My technology skills, as you are well aware, are not all that great. So, what happened last night did not exactly get saved. But that's okay because I think I can do a better job of explaining exactly what happened. So, those of you who were not able to be there last night, hopefully this will give you a sense of exactly what happened during our discussion. Besides the fact that you won't get to hear us sing happy birthday to Jesus, whose birthday is today, the 17th. But anyway, let's get started. So, the first thing I want us to think about with ozone depletion or ozone chemistry is we have to go back to the electromagnetic spectrum. So I've shared that with you, and I want to go through a couple of points on the electromagnetic spectrum. First of all, over to the left, you'll notice we have gamma rays and we have X-rays. Now, gamma rays and X-rays are completely blocked. Oops, sorry. Completely blocked. Stop. Go down. I don't know why that's doing that. By the magnetosphere. Okay, that means that all of these rays, everything on the spectrum, if you recall, are part of radiation, right? So this is all radiation. And the radiation that we receive is mostly from the sun, right? So almost all of it comes from the sun. That's our source of radiation. Now, radiation comes in different wavelengths. So we have our X-rays and our gamma rays that are those high energy rays that come in from the sun. However, our magnetosphere outside of the atmosphere is able to block those away. And that's one of the reasons why life is able to flourish on the earth, is because we don't have those radiation. Now, UV radiation right here. There's actually three kinds of UV radiation in terms of the wavelength. We have UVA, UVB, and UVC. Now, they get increasingly stronger or more. What am I trying to say? More energetic as you move away from the visible light spectrum. But those are what we have now. In terms of what the ozone layer does, the ozone layer blocks out UV, B, and C. So ozone layer blocks UVB and C. That means that UVA gets through to Earth's surface. Okay, so in other words, when you go out and lay in the sun, you're going to receive UV radiation, but it's going to be UVA that you get. So everything, that's the only form of UV radiation that reaches Earth's surface. UVB and UVC are blocked by the ozone layer. And what's going on here is they're actually being absorbed. Okay, so it's being absorbed. And I'll show you the reaction for how that happens here in a second. And then next we have our visible light. And you'll notice it's just a tiny, tiny little bit of what goes on in the electromagnetic spectrum. Infrared is next. And then microwaves and radio waves. Now, here's the distinction that I want you to think about. When you go out into the sun, a lot of times we get warm, right? The sun's warmth gets to us, and what's causing that is infrared radiation. Infrared radiation heats. Okay. UV radiation does not heat, so we're not going to feel hot from UV radiation. I want you to think about it this way. When you go and have X-rays done, and they fire that X-ray at your mouth, and you've got that big lead blanket around you. Do you get hot? The answer is no. So when we look at this, now it's going to do damage, right? That's why they cover you over. They don't want you to start developing mutations. But the infrared radiation is what's going to make you hot. Visible light doesn't make us hot either, if you think about that, right? Our eyes can pick that up, but it doesn't make us hot. Okay? So the reason why I want to emphasize this is that UV radiation is what happens, comes through, or UV radiation comes through when there is ozone depletion. Okay. Okay, so we've got that. So that's our first distinction. And in this case, it's UVB and UVC that's coming through. However, when we talk about climate change, infrared radiation causes heating. So when we have greenhouse gases, they trap outgoing heat. Now this is going to be important here in just a little bit, but you have to understand it's trapping outgoing heat. So the Earth itself is giving off infrared radiation. You are giving off infrared radiation. Ordinarily, those are going to leave, but because if you'll remember, we are an open system when it comes to energy, right? Just go back and just remind us again of all those things that we learned from the very beginning of Unit 1. So we are an open system to energy. Therefore, infrared radiation comes in, all radiation comes in, and then it can also leave our system as well. Okay, so now that we've covered the electromagnetic spectrum, let's move on and look at what's going on with ozone. So let's set up first of all, we're going to set up the Earth here. So we're going to draw an Earth down here. It's not going to give us enough room. Let me move down a little bit. Okay, because I'm going to come back. Okay, so we're going to have our Earth right down here. Go ahead and color it in. And the ozone layer covers the entire planet. All right, the entire planet is covered with the ozone layer. It goes all the way around us in the stratosphere. I'll talk about that here in just a second. But the ozone layer depletion that is occurring is in one specific location. And that location, is over Antarctica. So we're going to draw Antarctica out here on this surface. Now, there's some special things about Antarctica that we want to sort of set up exactly where it is. So we have a little bit of Africa coming in this direction. So just imagine we've turned the Earth upside down. Africa's here, and maybe South America is like, I don't know, like right here, right? So South America's coming in this direction. And then there's nothing. Australia's like way over here. And then around Antarctica is pretty much a big old nothing. All right, so let's go back and we're going to label this as Antarctica. And this is going to be important as we work our way through this. All right, so just as a reminder of how everything is set up, we have our first layer of the atmosphere. So we learned this in the beginning. We have our layer of atmosphere here, and that is called the troposphere. Okay, so we have our troposphere here. And then above that, we have the stratosphere here. Now, why is it called the stratosphere? It's called the stratosphere because it is striated or in layers. like an onion. All right, so what that means then is that inside the stratosphere, we have a couple of layers. We have, first of all, the lower level, and then we have our ozone layer that's coming through right here. So this is our ozone layer. Now there's still some more stratosphere that's above it, and we'll talk about what that means later. If you'll recall, when we talk about the troposphere, as you go up in the troposphere, the temperature decreases. Right, temp goes down as we go up. However, when we get into the stratosphere, just the opposite happens. So it's cold, right? It's cold, and then it's going to get warmer as we go up. So it's going to have layers of warmth. So we have warm here, and then it gets cold again up at the top. Okay, so that sort of sets up what we're looking at. We're looking at the troposphere and we're looking at the stratosphere. All right, so let's talk about what's going on inside the ozone layer. So I'm gonna put a divider in here just because we're gonna look at this in two different ways. Okay, so there's our divider like that. I don't really like that. Okay, we'll do it this way. All right, so we're gonna look at two different systems going on. The first one is what happens just in general with just what goes on inside the ozone layer. I think I lost a little line here, so let's put that back. All right, in the ozone layer, we have a reaction that occurs, and that reaction occurs like this. We have oxygen present, and we also have oxygen as just a single atom that's present. And what happens is that goes through a reaction and creates ozone. So ozone forms. But ozone is unstable. Okay. So if you'll recall when we talked about air pollution, we noted that in the troposphere, when ozone forms, ozone is forming from our NOxes and our VOCs on the tropospheric level to form ozone, right? So that's the reaction that's here. But remember, it's sunlight driven, all right? So in the ozone layer, it is also driven by sunlight. So we're going to put in here then our sun. Let's make it a little bit bigger. So we're going to have our sunlight that's going to come in here. So we have sun like that. All right, back to our illustration. So the sun, is going to emit radiation. So it's emitting radiation all the time, right? From above the stratosphere, it's emitting radiation. And what happens to make this reaction, this formation of ozone occur is UVB or C. Either one will work. Now it's going to cause this reaction to occur. Now it's unstable and it is also going to fall apart. Okay, so this is how it happens. It's just forming, unforming, forming, unforming, forming, unforming. You could also write it out like this. You could say O2 plus oxygen is going to yield O3, and then you're also going to have it just break apart. Whoops, that's a 2. Let's see if we can do it that way. You're going to have it do this, just like that. In both of these instances, they are going to form and reform because of UV radiation. So in this particular case, the UV radiation that's going to cause this reaction to happen is UVC. Okay, so in other words, we have the absorption of UV B or C on this one, and the absorption of UVC in this particular case. So basically what this reaction is doing, it is tying up the absorption of of UV radiation. So now, because of that layer right here, we no longer have UV radiation that is able to get to Earth's surface. All right. Now, this is what happens when we have no CFCs, or also known as ODSs, or ozone depleting substances. So this is what's going on without those things. All right, so let's come down here and talk for just a minute about our CFCs. So what does CFC stand for? It stands for chlorofluorocarbons. Okay, so what those look like are 3 chlorines plus a fluorine plus a carbon. Now, these chlorofluorocarbons were developed in around the 1920s. Okay, so they're not that old a chemical. Now, these were considered to be a marvel chemical when they happened, and they were, I think, developed with Dow Chemical, and they have a brand name, and that brand name by Dow was called Freon. Now, Freon is used much like you use Kleenex or Band-Aids or dumpster or anything like that. It is a brand name that kind of became universally used for those products. But they're not the only ones who developed chlorofluorocarbons, but they did own the rights to the name Freon. So what did they do with chlorofluorocarbons? Well, one of the things they discovered about chlorofluorocarbons is that they were non-reactive with humans. In other words, you could breathe them in and breathe them out, and they didn't do anything to you. So they are not a pollutant, okay? Not a pollutant in the terms of directly causing harm to humans. But what they decided that they were really good for was several different things. The first one is that they were really good coolants. Okay, so it was a good coolant. And they could use them then in products like refrigerators, and air conditioners as coolants. And I'll talk about why here in just a few minutes, about why that was such a great idea. The other thing that they could be used for was propellants. And the main way that they came into use here was in things like aerosol cans. So an aerosol can, if you think about what it is a can of gas with product inside of it, and it is being held at pressure. Well, there's some gases that you can use to hold things at pressure, but the problem is that many times they're flammable. So they would burst, if you held them under pressure, they might just burst into flames. They were unsafe to be used in such a small location inside that can. Well, the nice thing about fluorocarbons is that they were non-explosive. Okay, so this was huge because then we could use them in small spaces, in little cans, and they weren't going to cause anything to burst into flames. Very important when you're working with propellants. Okay, another thing that they were used for is they were good blowers. They were good for infusing product with air. So one of the things that they were able to do was they were able to develop something called styrofoam. So believe it or not, styrofoam is also a brand name. It's polystyrene. And styrofoam, what it is it's thick plastic, right? But it's been blown with air. And so the air that they blew into it was chlorofluorocarbons, or CFCs. That's what pumped it up. The other beauty that they got out of it is that it was able to trap heat. Okay, so when you have styrofoam, what it's really good for is it's a really good insulator, right? So you're going to insulate things with a styrofoam cup or a styrofoam container because it's now trapping the heat or trapping the cool within that product. There's some other things that they used it for. They used it in some pesticides. I'm not sure why, and some solvents. So if you'll remember from the video, those were the descriptions of what they did. Solvents, pesticides, refrigerators, aerosols, air conditioners, change that. And we're also going to add styrofoam to that as well. Now there was another product that was used, and those were called halons. Now the halons are a little bit different, but that was the one that was used in the firefighting equipment from the video. All right, so these are known as, I can't spell. Okay, so what these now, well, they were just produced. Now, they were produced in the 1920s and used extensively, but if you'll recall, as I've said before, after World War II, they had developed all of these products that they had been using for war machines and wartime things, and the country really went to work in a lot of chemical ways to develop these products. But in the process, what they did was they had to have another market. So in the 1950s, they started really ramping up the use of these chlorofluorocarbons. So they started selling us on products, things like refrigerators, air conditioners. They started selling a lot more of all of these products. So from the 1950s to the 1960s, there was a wide increase in the use of CFCs. All right, and everybody was loving it. It was meeting a lot of needs. We had refrigeration that we'd never had before. Before that, they'd had to use things like ice boxes instead of being able to have refrigeration within the home. So these are ways in which life was seeming to improve. But then in the 1970s, they noticed that something was happening. There was a problem. And if you'll recall from the video, they talked about scientists who were down in Antarctica, and they were measuring the levels of ozone over Antarctica. And when they were doing this, they were doing this in springtime. All right, so let's go back and look at what's going on in springtime. Okay. So, first of all, we have to understand that this is occurring in Antarctic spring. In Antarctic spring, whoops, let me try to take that off. Okay, Antarctic spring occurs in September to October. Okay, so those are the months in which they were seeing the ozone levels drop off dramatically. And what they described it as they described it as a hole in the ozone layer, as if someone had punched a hole through it. So at this point also and this was starting in the 1970s that they were discovering this was happening. So in the 1970s, they started to notice the hole forming over Antarctica. Okay, so what's going on? Why was it happening in the spring? Why spring? Well, there's some reasons for this. The first one is that if you'll recall, in winter over Antarctica, right, winter in Antarctica gets really, really cold. All right, so gets very cold. Now, why does it get very cold? There's a couple of reasons. One is no sunlight whatsoever. No sunlight, and this is due to the tilt of the Earth, right? So we are tilted away from the sun. So it was getting no direct sunlight whatsoever. So no radiation was coming into Antarctica. The other thing that happens, and this is called the polar vortex. So when you look at where Antarctica is situated, let's come here and change our color just a little bit. So what we have over Antarctica is, you'll notice there are no land masses around it, right? So the nearest points of land are quite a ways away. And so what happens is that the water and the air rising above the water starts to spin. And it starts to go around and around, right? Around and around. And what this creates is basically a superstorm over Antarctica. So it's isolated from the rest of the planet, and it's starting to get very, very cold, and it has these winds that are circulating around and around it. So this causes it to get very cold. And this is going to come in very, very important here in just a second. If you'll recall from the video that I showed you from the very beginning of this semester, Earth from Space, they talk about what happens on Antarctica that makes it so super cold and then causes that cold to spread out across the rest of the planet. One of the things that happens is, as it gets very, very cold, some clouds start to form. And those clouds start to form up here in the stratosphere. All right. And so they're forming basically over Antarctica. And what these are called, they're called polar stratospheric clouds. Okay, so they're slightly above the ozone layer, and they're forming when it gets really, really cold. So this is important because they're where a lot of reactions begin to take place that affect the ozone layer. All right, so let's go back here in just a minute. So in the 1950s through the 1970s, all across the planet, we were creating these CFCs. Okay, so the CFCs were starting then to migrate and work their way upward into the stratosphere. Okay, so they're moving on up into the stratosphere. And when they got above the stratosphere, they were here on those polar stratospheric clouds. Now, they're all across the planet once again. But because of the way in which all of this occurs, they sort of swoop down over Antarctica where it was getting really, really cold. So they're everywhere, but they're pretty much lighting up on these polar stratospheric clouds. Okay, so now we're going to talk about what's occurring with these polar stratospheric clouds. But the first thing we need to look at is what happens when you have our CFCs and ozone depleting substances, or ODSs. So we have our reaction occurring over here with ozone, like I'm showing over on this side, right? So the reaction that's occurring right here. But in this particular case, what happens is that our CFCs are Cl3, and our F and our C. Okay, so they get up here, and the chemistry is that this chlorine breaks away from the rest of the CFC. So it's going to leave the chlorine out there all by itself. So when we have our oxygen, our ozone here, okay, so it's up there floating around, but remember, it's not real stable, so it's going to start to break apart anyway, and it's going to break apart like this, okay? Now, in this particular case, what happens is that chlorine is going to come into this reaction. And what it's going to do is it's going to bind in this reaction. So now, rather than forming ozone, what we're going to have is we're going to have ClO form. So we have our oxygen and then our ClO. But this little girl right here, this chlorine, she's highly unstable. And so what she's going to do is she's going to break away again. Okay, so she's going to break away. But now there's not another oxygen to bind to it. So it's not going to, let's say we had more than one. So I'll show you here in a second what that's going to look like. So let's say we have two of these. So we have two chlorines, and they're going to break apart into two of these. Okay, so now you have two of them here, and so each one of them are going to let go of their oxygen, right? So they're going to let go, and when they do, they're going to bind to themselves like this instead of the three that we have over here. Now, oxygen as a gas is very stable, right? So they're not going to want to bind again to the lone oxygen because it's not really there. So now we have disrupted the system. We now only have oxygen gas and we no longer have our ozone. Okay, so that's kind of what's going on here. So we have without CFCs and we have with CFCs. All right, I'm going to explain a little bit about what's going on with our polar stratospheric clouds and without polar stratospheric clouds. This is sort of extraneous information, but I think it helps to kind of explain exactly what's going on. So when we have no stratospheric clouds, so in other words, if this system were without CFCs, it would be like this right here, right? This is what we would see. When you add in not only our CFCs over here, but you also add in your polar stratospheric clouds, you're going to have a slowing of the healing of this process. So let's first look at what happens if we had no polar stratospheric clouds and we also had some chlorine floating up here. All right, so let's say we have our PSCs here. We're got no PSCs. So our chlorine, what's going to happen is we're going to have that chlorine floating out there, and then we're going to have our ozone. And it's going to still, when the ozone breaks apart, it's still going to form this product. And then also this, right? However, this ClO, there's also present up here are NOx. Okay, and that's what's going on up in the upper atmosphere. So there's two ways in which chlorine can be captured without our PSCs. The first one is if our NOxes are involved, it's going to produce this compound. And it's going to hold it in. So now chlorine, she's captured, she can't go anywhere, she can't do anything. The other thing that could happen is that the chlorine could also bind with methane. Okay, so we can have with methane gas up here. And it's going to hold it or trap it in hydrochloric acid. And eventually that's going to fall back down to earth and everything is cool. So it's not, the chlorine's going to basically be taken away. When you have polar stratospheric clouds, here's what happens. So we have, first of all, our chlorine will go through this binding reaction with our NOx that's up there or our hydrochloric acid. So they're still present. But what happens then is that we're going to have visible light come into this. So we have our sunlight here. And visible light, which is penetrating, is going to cause a reaction to happen on the surface of the polar stratospheric clouds. And it's using visible light to make this happen. Right, so we have visible light that's getting through. And what it's going to do is it's going to break away the chlorine into chlorine gas. And then that's going to split up into two different chlorines like this. And now it can then bind with ozone again and cause this ozone destruction, right? So it's back to this little dude right here. All right, now we've doubled it. So if you'll recall from the video, they talked about how one chlorine atom can destroy lots and lots of ozone. And this is sort of what happens. Okay, so now we have it with our polar stratospheric clouds and without our polar stratospheric clouds. Like I told you, that's sort of extraneous information. So if we're going to bind this up in the clouds, right? Right like that. Okay, why does this matter when it comes to things like greenhouse gases? Okay, so we first of all have to go back and look at how polar stratospheric clouds are formed. They're formed because it gets super, super cold. Well, let's talk about what happens when we have greenhouse gases. All right, so we have greenhouse gases. Now, greenhouse gases do something. They trap heat. So what they're doing is they're going to hold the heat down in the troposphere, right? So they're trapping the heat in the troposphere. And what that does is once the heat gets trapped, it means that that heat can no longer escape like it had been before. It can't work its way up into the stratosphere. And so what happens in the process is that it causes the stratosphere to get colder. Well, as it gets colder, that's how you're going to have polar stratospheric clouds form. So the colder it gets, the more polar stratospheric clouds form. And that means that if we want to heal the ozone layer, we have to stop the polar stratospheric clouds from forming. And the way to do that is to lower our greenhouse gases. We have to lower them or take them out of the mix. Okay, I hope that makes sense the way I described it. If not, please ask me questions about this. So let's just sort of distill this. How are polar stratospheric clouds formed? Okay. They form because it must be cold. All right, now remember, when I say these are clouds, I'm not talking necessarily about water vapor clouds. They're clouds of real exotic products. If you'll notice, we have methane gas up there, hydrogen, and we have nitrous oxides up there as well, right? Or nitrogen oxides up there. So it must be very, very cold in order for those to form. And the way in which this happens is that our greenhouse gases trap heat in the troposphere, which in turn makes the stratosphere colder. All right, one more thing about why this happens in the springtime. If you'll notice, in order for this all to occur, you have to have sunlight. All right, so in Antarctica over the spring, what you're going to have is you're going to have this reaction right here occurring because of sunlight. All right, so sunlight is going to come along or UV rays are going to come along and they're going to cause this reaction to happen. So it's not going to happen in the wintertime. It's because it's getting super, super cold. But then once those clouds form and then the light hits it, and if you'll notice up here, the light from the sun is going to hit it on those clouds, and it's going to split apart that chlorine in order for it to destroy ozone. So what we have to do then is what they discovered was we have to lower our levels of chlorofluorocarbons. And the only way to do that was through a joint agreement with all parties involved. So what happened then was the Montreal Protocol. And the Montreal Protocol had to occur among all interested parties. All right, everyone had to agree in 1987 that this was valuable for us to all do, because we couldn't just have a couple of countries do this and not everyone else. Everyone had to agree. And it was sort of a lessening of things that occurred, but for the most part, all nations had to agree to stop using chlorofluorocarbons. Now, the hole is still there, and there's some reasons why. One is that CFCs take a long time to reach the stratosphere. Okay, so or the ozone layer. Oops. So they're going to take a while to get up there, right? So in order for us to do some work, we're going to have to think about, okay, how long is this going to take? And we are seeing results. Okay, so it's been now 35 years almost that this happened, and we're seeing that hole is getting smaller and smaller and smaller. We're hoping to get back to pre-1970s levels in the next, 20, 30 years. We've had some years that are better than others. This year was really good, but they called it sort of an anomaly. It wasn't necessarily because it's working so much quicker. It's just that, the situation was the conditions were a little bit better. We had less polar stratospheric clouds, essentially. So they take a long time to reach. The other thing is that one chlorine can destroy many ozone molecules. So we can break them apart over and over and over again. The other reason why this is slow is that CFCs last hundreds of years, okay? So they estimate that they can last like 500 years. So they're going to be up there for a long time, okay, breaking apart up in those polar stratospheric clouds. So it was really important that we get on top of this as quickly as possible. But the problem is that you had this miracle chemical, right? You had this CFC that was so efficient. Now, think about this just a second. I'll talk about that here in a second. What do we do? Like, do we just suddenly stop using refrigerators and air conditioners and aerosol cans? So they said, no, let's don't do that. Let's replace them. So we're going to replace CFCs with another gas, another human-created gas, HFCs. Now, I want you to think about something a second. If you think about all the pollutants that we talked about, almost all of the ones in air pollution were naturally occurring chemicals, right? One of the problems and why these things take so long to break down is because they are human-made. All right, we don't have a feedback loop to deal with these things. So when we introduce human-made chemicals into our environment, we don't have any way of dealing with them. Nature can't help us with this. We have to figure out another way. So the CFCs were replaced by HFCs. Now, HFCs are not ODSs. Okay, so that was the whole goal. How do we quit making an ODS? Well, we come up with a different way. But then we discovered a problem. CFCs and HFCs are greenhouse gases. And I'm just going to put a little sad face. So they discovered that they were actually greenhouse gases. In fact, our HFCs, while the CFCs may last hundreds of years, HFCs have been measured to last tens of thousands of years. So, what are we going to do? Now, because think about it just a second. If we go back up here, we have greenhouse gases, they're trapping heat. Now we put our CFCs and our HFCs in there, and what do we got? Well, now we have even more heat being trapped, which then leads to more polar stratospheric clouds. So we've got to do better. We have to do better. So what they've done is that they had to actually come along and replace these gases, right? So these have been replaced by something that has less greenhouse potential. And we'll talk about greenhouse potential when we get to our talk about climate change here in just a little bit. But some really important key things to remember: that ozone depletion doesn't have much to do with making the planet hot. However, making the planet hot has a lot to do with how slowly the ozone hole can recover. Okay, so they're kind of tied in together, and the video talked about how those as the pole gets colder, or the polar vortex happens more and more, it is actually drawing wind currents toward the poles, and that also is leading to climate change. So there is some connection, but it's not related to trapping of heat necessarily. Okay, I think that is about all that we need to cover. If you have any questions at all, please let me know.